Hi, welcome. We are going to get started on our review multiple choice of all things, for the most part, nuclear. You should have your reference tables and probably a calculator because we're going to be working on some half-life problems. All right, so let's get started with question number 1. So the graph below represents a decay curve of a radioactive isotope. The half-life of this isotope is, so now to figure out what the half-life is, I need to figure out how long it takes in time, right? So our time axis is here. How long does that take to get cut in half? So then if I find the starting mass of 10, and then I go down this curve until I get to the mass of 5, which is right about here, how long does that take? Well, between 20 and 40 years. So between 20 and 40 is 30 years. All right, easy? Nice. Okay, that is a decay graph. Okay, so now let's look at our next one. What is the number of hours required for potassium-42 to undergo 3 half-life periods? I don't even know what the half-life of potassium-42 is. Is there a way that I could find out that information? Yes. So I need to find potassium-42 on table N. And so here's potassium-42 on table N. Where are you, potassium-42? Yep, right here. And then that is 12.36 hours. So if I go back here, it's not going to be this one because that's 1 half-life. So I need to do 12.36 times 3 because that's 3 half-lives. So it's going to be 37. So it's going to be D. So this question might be a little bit older than 2011, but the half-life is pretty close to what the 2011 reference tables say. All right, so an original sample of a radioactive isotope, I'm going to just move this up, and I'm going to go like this, so maybe I have some more space. All right, so an original isotope has a mass of 10 grams. After 2 days, 5 grams of the radioisotope remain unchanged. What is the half-life? All right, so for half-life, I'm going to set up a chart. You can go across or down. I like to go down. It doesn't matter. Across is fine as well. So I'm always going to start with time and some kind of mass or amount. Time always begins at 0. So I'm always just going to start off with time, mass, times 0. Now I'm going to take whatever I have in the question, I'm going to fill in my chart. So it has an original mass of 10 grams. So that's at time 0, I have 10 grams. After 2 days, so that's my end time, 2 days, I have 5 grams left. So now I have to figure out what the half-life is. So I need to know how many half-lives went by. So I went 1 half-life because 10 divided by 2 is 5. So it's 1 half-life took how long? 1 half-life took 2 days. So the half-life is 2 days. Easy? Okay. All right. So a radioactive element has a half-life of 2 days. Let me just do a little bit of erasing here. Okay. Has a half-life of 2 days. Which fraction represents the amount of the original sample of this element remaining after 6 days? Okay, so I'm just going to set up a chart over here just so it doesn't get into the way of anything else. Oops, weird. All right. Oh, sorry, I'm too close to the edge of my screen. That's why. All right, so time and mass. All right, sorry for the messiness. Okay, so the radioactive time always starts at 0. A radioactive element has a half-life of 2 days. So 2 days is the first half-life. What fraction represents the amount of the original sample of this element remaining after 6 days? Okay, well, 1 half-life is 2 days, and then another 2 days becomes 4 days, and another 2 days becomes 6, right? There's my end time, 6 days, right? 6 days is my end time. I need to figure out what fraction. Well, if I'm ending with a fraction, I'm starting with a whole. So I'm starting with 1. So then divided by 2 is a half, right? So after 2 days, there's a half. Then after 4 days, a half divided by 2 is a fourth. And then I have a fourth divided by 2 is an eighth. So I have 1/8. Are there other ways to do these problems? Absolutely there are. I'm just showing you one way to go about doing it. And remember, you can make a chart that goes across. It doesn't have to go down. It's the same thing, just a different perspective. All right, which of the following radioisotopes has the shortest half-life? Well, do you ask yourself, like, looking at those elements, say, how am I supposed to know that? Well, then that's where you go to your reference tables and you figure out, well, which one has the shortest half-life. So then you're just basically going to compare and you're going to look at whichever one has the shortest half-life. So make sure that you're carefully looking at units because some of these are in days, years, ms, right? Over here for calcium-37 would be milliseconds, right? So then we have all different ones. So let's go and take a look at which ones we're looking at. So carbon-14 and hydrogen, potassium, and phosphorus. So carbon, hydrogen, potassium, phosphorus. So we're looking at carbon, potassium, and hydrogen, and phosphorus. Let's check to make sure that's the right potassium. Is it 37? Yes. Okay. So which one has, are we looking at the shortest or the longest? Shortest half-life. So I'm looking at, 5,715 years. That's not very short. 12.31 years. So I'm going to eliminate carbon because hydrogen's already shorter. So now between hydrogen and potassium is only 1.23 seconds. And then phosphorus is 1.28 days. So it's going to be, it's not going to be that one. It is going to be the potassium because it's only in 1.23 seconds. So it's going to be the potassium 32. Let me double check to make sure that there was only one potassium. Potassium, not phosphorus, right? So potassium 37. Oh, sorry. Okay. I was thinking potassium and I circled the P, right? Remember, this is why you have to be really careful. It's easy to make that kind of mistake. All right. So number 6, the half-life of a radioactive isotope is 20 minutes. So there's my half-life, 20 minutes. Okay. What is the total amount of a 1 gram sample of this isotope remaining after 1 hour? Okay. So I'm going to set up a chart. Oh, look, I have a line right here. I'm just going to do that. So just going to do T for time, M for mass. Time starts at 0. So the half-life is 20 minutes. Okay. So there's where my half-life goes. I'm looking for how much remains, down here, after 1 hour, my end time. And I'm starting with 1 gram sample. I have 1 gram at time 0. So I have 1 gram at time 0. So then 1 half-life, right? I'm going to go down 1. That's going to be a half, right? Which is 0.5. So after 20 minutes, I have a half. So, am I at my end time of an hour? Nope. Add another 20 minutes. What do I have now? I'm at 40 minutes. So now a half becomes 0.25, right? And then 40 plus another 20 minutes gets me to that hour. And then I have 0.25. And then I'm going to divide that by 2. And that's going to be 0.125. And then here's my ending amount, 0.125 grams. Easy? Not easy? Keep practicing. It's the only way to get better. So let's move up to the top and let's look at our next set of questions. Okay, number 7. What is the number of half-lives required for a sample of a radioactive material to decay to 1/16th of its original mass? Okay, so when we're doing fractions, you start off with 1. And then you divide it by 2. That's 1 half-life. That's a half, right? So then I'm going to divide a half again, and it's a 4th. And I want to know what is the number of half-life periods required to decay to 1/16th. That's my end time. A 4th divided by 2 is an 8th. An 8th divided by 2 is a 16th, right? 1/4, 8th, 16th. So then that took 1, 2, 3, 4 hops for half-lives. Okay, so question number 8. What is the total number of grams of a 32-gram sample of phosphorus remaining after 71.5 days of decay? Okay, so I'm going to set up a chart. Okay, time and mass. The time always starts at 0. And then I'm starting with 32 grams. So 32. I don't know the ending amount. And I know my end time is 71.5. So I'm just going to do a 71.5 down here. Okay, so 71.5. So now I need to know what the half-life is so I can figure out how many half-lives to get to 71.5. I don't know the half-life of phosphorus 32, but I do know a place where I can find the half-life of phosphorus 32, which is my reference tables. So if I find phosphorus 32, right? That's the one that we already had circled. That's 14.28 days. Okay, so after 14.28 days, right, that's my half-life. So then 32 divided by 2, right? Now that's at 16 grams. Well, I need to keep going because I need to get to 71.5 days. So then I have another 14.28, right, days. So 14.28, right, plus another 14.28, which I'm doing on my calculator. So now is 28.56. So 28.56. So now that 16 gets divided by 2, that's an 8. So now am I at 28.56 is not at my 71.5 days. So I really need to add another half-life of 14.28, right? Because another 14.28 years goes by. And now I've got 42. Oops, let me erase this. All right, so now I'm at 42.84. And that 8 becomes a 4. So now I'm still not at 71.5, so I'm going to add another 14.28. And now that gets me to 57.12. And now that 4 becomes a 2. Am I at the end life yet? Nope, because I'm looking to get to 71.5. But right now I'm only at 57.12. So now I'm going to have to add another 14.28. And then that gives me the 71.4, which is basically 71.5. And that 2 becomes a 1. So then 1 gram. And again, are there other ways to do half-life problems? Absolutely. Do you have to do them this way? No, you do them whatever way you feel the most comfortable with. Okay, so I'm going to have to make this a little bit smaller. If my computer will, there we go. So question number 9, base your answer to the following question on the graph below. The graph represents the decay of radioactive material X into a stable decay product. Okay, what is the approximate half-life of radioactive material X? So if I look at this graph, right, so the dashed line is showing me the decay, right, starting off at 100, getting all the way down this curve, okay? So then that is my radioactive material, right? That's going down. But the decay product, what it's transmutating into is going up. So now I'm just going to erase my lines, okay? And I'll erase that too. So I need to figure out what the half-life is. So if I start off with 100 grams, and I start off here at 100 grams at time 0, and I go over to 50, right? Because 100 divided by 2, right? That's a half-life. So then I read down, and that should take me 5. Oops, don't forget this. Read your axes. So if I have 5 now times 10 to the power 3, I need to figure out which one is that. It's not this, it's not this. So which one is that? That means I'm moving the decimal place 3 places, to the right because it's a positive exponent. So that's 5,000. Okay. All right, so question number 10. All right, let's take a look. Which sample will decay least over a period of 30 days? All right, somebody took the time to italicize a word. Pay extra attention. So decay the least, is that going to be the shortest half-life or the longest half-life? What do you think? It's 50-50. Okay, so if it's decaying the least, it is going to be whichever is the bad spelling, longest half-life. And how do I know which one has the longest half-life? Are you asking yourself, how am I supposed to know that? Well, then you go to your reference tables, and I'm looking at gold, phosphorus, iodine, and radon. So I'm looking at gold, iodine, phosphorus, and radon. Radon is 3.823 days, 14.28, 8.021. So then these are all in days, right? So then I've got 3 days, 14 days, 8 days and 2. I believe it's going to be our 14 because that's the longest half-life. So then it's going to be phosphorus 32. Where are we? Phosphorus 32, C. Okay, so let's move on to our second page. Okay, so here we have a decay series, which looks like the kind of one we did in your notes, right? I want to determine the fraction of an original sample of radon 222 that remains unchanged after 7.646 days. Well, first of all, according to this graph, we have radon 222, right? So is radon atomic number 86? Well, let's go to your periodic table. Radon is number 86. Okay. So then that one's over here. Okay. So then this is radon 222. Okay. But it's telling me the fraction. So this isn't necessarily figuring out the decay from this graph. I need to do a half-life here. So I'm going to do my time versus mass. Time always starts at 0. Okay. I'm determining the fraction that's remaining. If I'm determining the fraction, I start with a whole. And I'm ending at 7.646 days. And I'm figuring out what the fraction is. So first of all, I have to figure out what the half-life is of radon 222. So is radon 222 in my reference tables? Let's check. Let's go back to my table N. And radon 222. Let's see if that's in here. Radon 222 is there. And here we have in 3.823 days. Okay, so we have a 3.823 is my half-life. So after 3.823 days, 1 becomes a half. So now I have to do another half-life, right? So 3.823 plus another 3.823 days. And now that gets us to, oops, I think I did a math error. Right, 3.823 days plus 3.8, oops, I can't do this calculator thing, kids. 3.823 plus 3.823. It's kind of hard to type on a calculator and talk at the same time. All right, that gets me exactly to 7.646. So then a half becomes a fourth. So then I have 1/4 remaining. Okay, so 2 more questions. All right, we're doing it. All right, if a radioactive material were cut into pieces, the half-life of each piece would be, well, if I cut it into pieces, both are still radioactive. So the half-life is never going to change because it's always going to be the same. Never changes. Not even heat, not even temperature, pressure, nothing. Half-life is always constant. Right? So that's how we can measure time, right, with radioactive elements. Okay, so question number 13. Uranium-238, a solid, is naturally radioactive element found in the Earth's crust. As it decays, one of the products is radon-222, which is a gas and is very radioactive. Write the equation for the decay of radon-222. Okay, so I am going to, just since I've got more space down here, I am going to just do this right down here. I'm going to do A over here. So I have radon, I have 222, and it's going to decay. And I need to write the decay. Whenever I have a decay, I'm always going to produce a particle from table O plus a daughter nucleus, right? So the new element that radon is going to transmutate into. It does not say in my question what kind of decay that radon 222 does. So I need to go to my reference tables and I need to find radon 222, right? So here's my radon 222. It undergoes alpha decay. So that means I need to produce an alpha particle. So then that's what I'm going to write over here. I'm going to write an alpha particle, 4, 2, He. Or you could use the alpha symbol. So now the next thing I need to do is I need to figure out what is the nucleus that it's going to turn into, right? I have a top number, a bottom number, and a symbol. So the top numbers have to be equal on both sides and the bottom number, right? The law of conservation of mass and charge. So at first I need the atomic number of radon, which they don't give you over here in table N. You got to go over to table O to over here. So radon is right over there, and it is atomic number 86. Okay, so I get an 86 on the bottom. Okay, so I have a 2 on this side, and I have an 86. What number plus 2 equals 86? I'll just do 86 minus 2. So then that's going to be 84. Okay, I've got a 222 on the left and a 4 on the right. What number plus 4 equals 222? Or take 4 away from 222, right? So then I'm just going to do 222 subtract 4. And just to make sure I'm right, I'm doing it on a calculator because you never know. That's 218. Now I need to go, that's a terrible looking 8, but you'll forgive me. So now I just need to go to the reference table's periodic table, and I need to know what's the atomic number 84, right? Which one has 84 protons. So I have to change here. So then that's going to be 84, and that's going to be right here. So that's going to be polonium. So I'm just copying down the symbol, PO. Remember, the top numbers in these decay equations may not be the same as the top numbers of mass on your periodic table. Because remember, on your periodic table, it is an average atomic mass, right? So then that's a weighted average, right? These are isotopes. Okay, so we're going to go on to question number B. The half-life of radon 222 is 3.82 days. How many grams of a 1 gram sample of radon 222 will remain unchanged after 7.64 days? I feel like we just did something like this, didn't we? Yeah, didn't we just do radon 222 up here? So after 7.646, it's a fourth. So it's only going to be a fourth of the radon 222. But let's pretend we didn't have that question, right? So I'm just going to set it up. Time and mass. Time always starts at 0. And I want to know how many grams of a 1 gram sample remain after 7.64 days, right? I did my starting time and starting amount, and now my ending amount is unknown, and my ending time is 7.64. So now the half-life from 0 to 3.82 days is 1 half-life. So then 1 becomes a half, right? So 1 gram becomes 0.5 grams. So then I add another 3.82, and that brings me to my 7.64. And then my half becomes 0.25 because I divided that in half. So then 0.25 grams is my final answer. All right, so let's see. What do we have on our next page? Oh, big, long reading thing here. Okay, whenever I have one of these big, long reading segments, I kind of just read the question first, and then I'm going to go back to the reading. So then I want to see, how is the radioactive decay of krypton-85 different from the radioactive decay of americinium-241? So basically, I'm looking for something in this reading or something in my reference tables that talks about krypton-85 or americinium-241. So now let's go through the reading, and I'm just going to scan through, and I'm going to look for, so if I go through, walk through the front door, look up, and you'll see a smoke detector that owes its effectiveness to the constant source of alpha particle emissions from americinium-241. So americinium-241 undergoes alpha decay. All right, so now let's see if we can find something about krypton-85. As long as the gases remain ionized, electricity will flow. So indicator lights on your appliances may use krypton 85. Okay, krypton 85. And electric blankets, promethium 147, and fluorescent lights, and thorium 229. Even the food we eat is radioactive. The more potassium-rich foods, radioactive isotope, blah, 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 blah. Do I know? I know the decay of americanium-241, but it didn't say anything about the decay of krypton 85. Well, I don't think so, but maybe my reference tables will tell me something about the decay of krypton 85. Aha! Yes, I have krypton 85, and it undergoes B minus. If you forget what B minus means, I go over here and I see the B minus is right over there. And that's a beta particle, so it's beta decay. So then this undergoes beta decay. So how are they different? Krypton 85 undergoes beta decay. Americanium-241 undergoes alpha decay. That's it. You can't say that they have different half-lives because that doesn't answer the question. That doesn't answer the question about the radioactive decay. Okay, so base your answer to the following question on the information below. Radioisotopes carbon-14 and nitrogen-16 are present in a living organism. Carbon-14 is commonly used to date a once living organism. Explain why nitrogen-16 is a poor choice for radioactive dating of a bone. Well, let's see. I need to know something about carbon-14 and carbon-16, but it doesn't really tell me anything about carbon-14 and carbon-16 other than carbon-14 is used to date once living thing. So if you say, how am I supposed to know that? Check your reference tables, right? So even if you're just matching anything in your reference tables to anything in your question. So carbon-14 and nitrogen-16. Let's see what they have on table N. Okay, so let's just erase so I can see what I'm doing. Okay, so let's make ourselves a little bit bigger. So I have carbon-14, which is right up here at the top. And there's my carbon-14. And now I have to find where my nitrogen-16 is. Here's my nitrogen-16. All right, so carbon-14 can be used to date bone. So they both undergo the same kind of decay. So I can't use that. That's not going to help me differentiate the two because they're the same. So the only thing that's going to help me differentiate is those half-lives. Carbon has a half-life of 5,715 years. Nitrogen-16 has a half-life of 7.13 seconds. So the nitrogen-14 just decays too fast. So then nitrogen-16 decays too fast. So, or it has the half-life is too short. Okay, so this is going to wrap up our multiple choice and some of our short answer practice. So you should be all set to go on to CASEL learning assignment and test or repractice. My suggestion would be to go back through some of these questions and try them again and see if you're still getting the answers right. Right, the more you practice, the better you will get at these questions. So I'm going to close all tabs and I will see you for our next video.